second tutorial on quantum theory, which is on conceptual issues. Yeah, I found two quotes which I actually find quite adequate. The first one is, when one speaks to another man who doesn't understand him, and when the man who's speaking no longer understands, it's metaphysics. And the second quote is from a paper by Chris Fuchs, and he said, the issue remains, when will we ever stop burdening the taxpayer with conferences devoted to quantum foundations? I have no answer to the second question, but we may run into the danger of the first question.
I think when the Star Wars project gets abandoned.
Okay, a few general remarks is that we will be concerned with the conceptual aspects of quantum theory, and these do include what you could call metaphysical or philosophical questions, as well as interpretational issues. This is also on the relation between the mathematical formalism and the physical theory as referring to the world, whatever this means. And this is quite different from taking a mathematical formalism and well, getting some perspective on it from a mathematical point of view. It's really about what does the formalism tell us about physics, and this is where the problems are. It's not that the physicists don't understand how to handle Hilbert spaces or anything like that. It's really about the question, what picture of the world does emerge from the theory, if any. And this kind of problem, this is why people are interested in this, even after 80 years of discussion, even if you can't get any jobs with that. And there's no consensus on these issues, and of course I cannot promise that I can do more than present the problems, actually. We will see a number of mathematical results, which are of course all well known, and some of them are interesting as mathematics, and some of them are very straightforward actually as mathematics. But the main point is that we want to talk about the physical content, the physical meaning and consequences of these mathematical results. And this is also a reason why we will typically concentrate on the simplest mathematical setting in which these results can be obtained, which typically is finite dimensional Hilbert space, as we saw in the first talk. Of course, the infinite dimensional case will bring lots of additional difficulties. I want to some sources and references that I used, and this actually is quite useful. It's online. It's called the Stanford Encyclopedia of Philosophy.
I'm sorry, Louis.
This, but,
could you sit to the side of the camera? Would you mind?
Okay, where is it?
I think there. Yep, that's fine. Sorry.
And despite that this is called Encyclopedia of Philosophy, the articles on physics are pretty decent. I mean, it's of mixed quality because it's not a single author, but it's pretty good, and it's better than Wikipedia usually on these issues. The second one is not just because I'm working with them, because it's really a good book on the foundations and actually pretty basic stuff, how quantum theory is as a mathematical formalist, but also what it means physically and what conceptual questions are, is this little book by Chris Isham. This is the standard reference on what you could call the measurement problem. It's 25 years old now, of course a lot of stuff has happened in between, but still Wiener Zurich is a nice book. And if you've never seen it, look at the title and you'll see Bohr and Einstein smoking and discussing quantum theory. It's a very nice picture.
It's a big one in a collection.
It's a big collection of papers on these problems. And I don't think I'm crazy because this is a popular book. Well, it's somewhere between a popular book and actually it's a pretty serious popular book. Well, it has an excellent part on quantum theory and the conceptual aspects of it. So have a look at this if you like. I will, of course, also go back to the original papers, which is a very good idea in this field, because there's an enormous amount of secondary and tertiary literature, and it's very hard to understand problems if you don't get back to the original paper. Read the original papers, and I'll give you all the references. There's not too much, it's basically this small part of paper. These people knew that a good paper is pages maximum. And they're pretty easy to read, but it's very interesting. I want to start with the so-called Copenhagen interpretation, which is that interpretation which comes back to Bohr, Heisenberg, Born, and others. And you could call this the orthodox interpretation, and it's still prevalent and most popular among working physicists. Probably not among people in foundations, but working physicists usually are somehow.
Can I say something historic? Something I recently learned is that the Niels Bohr Institute, which is Copenhagen, which is the reason for the name, was fully funded by Carlsberg beer. Everything there, fully funded.
Almost everything in Denmark is funded by Carlsberg.
Yeah.
We should
So
call
it
it the
should have been
Carlsberg
the
interpretation.
Carlsberg interpretation or something.
Maybe you could ask them if they were once interested in funding this.
That's why I learned about it.
Most of you will have seen it, but Bohr is, of course, the leading intellectual figure in the development of the Copenhagen interpretation. Well, he usually is quite hard to read, actually, and he actually allegedly said that express yourself more clearly than you are able to think, and he did. On the other hand, what we call the Copenhagen interpretation today mostly goes back to Heisenberg more than to Bohr himself. And what did most of this? I just want to give this as a reminder. What's the absolute mathematical skeleton of quantum theory? What is really essential? I mean, there are lots of developments from this, but physical system as seen as a quantum system is described at least by, first of all, a separable complex little space H. Separable just means its countable basis. Well, then you have a unit vector psi in H, which is representing the state of the system, and physicists often call psi the wave function. I try to incorporate some of the physics lingo also in this, because this is another obstacle when reading literature as a mathematician or a category theorist who will maybe not know what wave function. It's not obvious why vector and Hilbert space should be called a wave function. This goes back to, well, the kind of Hilbert spaces people were looking at the time, but I won't explain this in more detail. What we also have is a set, this is A of S, where S is always a system of self-adjoint operators on H, and these represent the physical quantities like position, momentum, energy, spin, all these things. And then there's something, I think this wasn't mentioned before, this is quite important actually. It's called the eigenvector-eigenvalue link. What does this mean? Well, if I have some self-adjoint operator, operators will always have a hat. That's how physicists write operators. For example, if I want to talk about a physical quantity as an abstract thing like energy, I would write just A without a hat. And I want to talk about the operator representing this, and I'll write A hat. Okay. Suppose we have some self-adjoint operator, and we have a state psi such that A applied to psi is A psi. That is just, psi is an eigenvector, what's called an eigenstate of A. Then the physical quantity A represented by the operator A has the value A. That's a pretty basic thing, but that's an important aspect of formalism. If I measure the physical quantity A, this is more general than this, and do not suppose anymore that psi is an eigenstate. If I measure physical quantity A, the state collapses into an eigenstate of the operator A, and collapses to that eigenstate that corresponds to the measured eigenvalue of this operator A, so A lies in the spectrum.
So it's a different way to formulating the spectral decomposition.
You see there's a little more detail. This is the Born rule, basically. Okay, the Born rule allows to calculate probabilities of these outcomes, and so we want to calculate so-called expectation values. So this is the very basic stuff. If there are questions at this point here.
Sorry, you're going to have to remind me what you mean by self-adjoint again in terms of
Okay, self-adjoint is the following. You have a Hilbert space, you have inner product. So let's say you have the following thing. Do you know Dirac rotation? You didn't hear the first talk.
I wasn't in the first one, so...
Okay. You do the following. You have this operator A, and it acts on psi. Maybe some other vector. And then you form the inner product with psi.
Oh yeah, it's the same on the other side.
And then there is always another operator, which is the adjoint of A, which, if you like, acts here.
You probably shouldn't be calling them both psi. One should be psi and one should be phi.
Yeah, okay, that's true. Actually, they suffice.
Yeah,
It's equivalent. It's fine, you recall my memory of this.
Okay, yes, you're right. You can... let's say, pull this one phi. For every operator A, there's always this A dagger, which is called the adjoint, and operators for which A and A dagger coincide are called self-adjoint. Okay. So this is the formalism as it was set up 1925 roughly, and this is also what Bob used all the way in history. But what does it actually tell us? What was the physical interpretation of this? I want to emphasize quite a lot. This is very different from classical physics. First of all, the state psi of a quantum system has quite a different role from the state S of a classical system. Psi can be seen as a pure calculational device, encoding the observer's knowledge about the quantum system. This is a positivist approach, if you like. We don't say psi describes reality, it doesn't describe the quantum system itself, it rather describes what I know about it. And they're using quite a lot of these big words, you could call this epistemological. Or others saw the state vector psi as a symbolic representation of the quantum world, and we see in more detail in the next slides how we saw this. What all this is in contrast to classical physics, where the state actually gives you a literal representation, a pictorial representation, so you could say that the state in classical physics just tells you how things are, and every physical quantity has a value. And if you know the state and the dynamical law, well, you can roll it to any later time, you know sort of physical quantities at a later time. In quantum theory, the quantum state does not assign values to all physical quantities at once. You can say it assigns values to all those physical quantities in which the state is an eigenstate. For all others, do not get fixed values. And if you prepare a system with the same state and measure a physical quantity of which the state is not an eigenstate, then in different runs of your measurement you will get different results. And the formalism of quantum theory actually fundamentally restricts the possibility of assigning values to physical quantities. We see this from the uncertainty principle and later on Specker theorem in a more general way. So measurements in quantum theory do not simply reveal pre-existing values of physical quantities. And this is very important to understand. This is also why measurements are so important. Okay. So now I'll do something, I hope I won't bore you too much. This is quite a lengthy list of properties things that, taken together, give a certain interpretation of the quantum theoretical formalism. But it's very hard to summarize this. I actually took this from the article, Copenhagen Interpretation of Quantum Mechanics from the Encyclopedia of Physics. I just added a few comments. Now, this is Bohr's view on quantum theory, and it's worthwhile going through this once, even it's quite long. There's 2 more slides of that kind. But I want to do this just to show how strange this really is and why people are not happy with this. Okay, maybe you're happy with it. Okay, so let's go through this one by one. First, Bohr says, basically this is a reading of Bohr. This is not actually quoting from his papers, but this is what people took from it. It sounds quite reasonable. First of all, the interpretation of physical theory has to rely on an experimental practice. And secondly, the experimental practice presupposes certain pre-scientific practice of description, which establishes the norm for experimental measurement apparatus and consequently what counts as scientific experience. So far so good, but it strongly emphasizes that not the mathematical formalism is the primary thing, but actually what we do in the laboratory is primary. Our pre-scientific practice of understanding our environment is an adaptation to the sense experience of separation, orientation, identification, and re-identification over time of physical objects. This pre-scientific experience is grasped in terms of common categories like things' position and change of position, duration and change of duration, and the relation of cause and effect, terms and principles that are now parts of our common language. And these common categories yield the preconditions for objective knowledge, and any description of nature has to use these concepts to be objective. And if you see this in a philosophical or metaphysical way, then this is basically a neo-Kantian view. There are certain categories of thinking, if you like, that are necessary to do physics at all. And the second part of this is this. Bohr says roughly the concepts of classical physics are nearly exact specifications of the above categories. So classical physics is what arises from basically formalizing what we more or less accepted on the last slide as preconditions for doing physics at all. So certain categories of thinking, if you like. The classical concepts and not classical physics itself are therefore necessary in any description of physical experience in order to understand what we are doing and to be able to communicate our results to others, in particular in the description of quantum phenomena as they present themselves in experiments. So this is a very important point, because it just says you can't even talk about the quantum system but only in classical terms. And this is very important in understanding what the Copenhagen interpretation is. And then this is, well, he says this is why quantum theories differ from classical physics. He says Planck's empirical discovery of the quantization of action, and here what is meant is that the quantum of action is actually h bar, this famous thing. This gives a certain limitation how systems can interact. Well, this requires a revision or a foundation for the use of classical concepts, because they are not all applicable at the same time. The use is well defined only if they apply to experimental interactions in which the quantization of action can be regarded as negligible. This actually is a very, very small thing, this quantum of action. So for macroscopic objects, usually you can simply forget about it. So then we can apply classic concepts right away. But if you really look at small systems, atomic scale or smaller, then this is very important and cannot straightforwardly apply the classical concepts. Namely, in experimental cases where the quantization of action plays a significant role, the application of a classical concept does not refer to independent properties of the object. Rather, the ascription of either kinematic or dynamic properties to the object as it exists independently of a specific experimental interaction is ill-defined. It sounds quite comical, but this is actually a very radical statement, because it really tells you that you have to specify the whole experiment, the whole setup. Then you can talk about a certain kind of property, and then one which is tested by experiment. It doesn't make sense to talk about, let's say, energy before you actually have something there which measures energy. And what will become clear little later is that there are experimental setups which give you different kinds of information, different pieces of information about the system, but they're mutually exclusive. You can, for example, know about the position of a particle if you measure the position, then you lose all information about momentum, and the other way around. And it doesn't make sense to think, well, that the particle actually has a position, has a momentum. Bohr says it doesn't even make sense to talk about this before you have the setup, which realizes the measurement of either of these. And you can't have a setup which realizes the measurement of both of these. The last point on this slide is that quantization actually demands a limitation of the use of classical concepts, so that these concepts apply only to a phenomenon which Bohr understood as the macroscopic manifestation of the measurement on the object. That is the uncontrollable interaction between the object and the apparatus. This is another idea that measuring microscopic or quantum object is disturbing in an uncontrollable way. Okay, if you want some kind of slogan for this, you could call this some kind of contextuality, and either experimental or environmental contextuality is what is expressed here. So it's really important to understand that this gives very strong constraints of what we can actually say about a quantum system. We can say very little about a quantum system in itself. Actually, formalism is not adapted to doing that. Formalism, quantum theory, is describing what you get if you prepare a certain apparatus which does a certain measurement on your system.
I've got a question. Like, if you take a piece of wood and you're curious to know whether it burns or whether it floats, and you would assume that if you got this piece of wood classically, you would assign the properties it burns or not, or it floats or not to it. How would you test that? Because if you test one, you can't test the other.
Well, you could make it float first and then dry it out. And then and you assume that
this might have affected this
you
properties.
can dry it out while affecting its properties only negligibly.
That's a good answer. I can't do that. Okay, this is the last slide of the common points.
That was very sneaky.
Okay. Furthermore, Bohr says the quantum mechanical description of the object differs from the classical description of the measuring apparatus, and this requires that the object and the measuring device should be separated in the description. The line of separation is not the one between macroscopic instruments and microscopic objects. It has been argued in detail that Bohr pointed out that parts of the measuring device may sometimes be treated as parts of the object in the quantum mechanical description. This is not very clear to me, actually. This is pointing to a famous difficulty, namely, if I have a measuring device and I need to talk in classical terms about the quantum world, well then basically this means my measuring device is not a quantum object, it's a classical object. As well as me as observer, I'm also a classical observer of the quantum world. Well then you wonder, because measuring apparatus is a physical system itself, why shouldn't it be described by a wave function? And so there's this famous discussion about the cut, whereas actually the border between the quantum world and the macroscopic world. And I would agree that size alone cannot be the right thing to look at. There are today, Bohr didn't know that, but today we have Bose-Einstein condensates which contain 1 million atoms. And you actually can see them with your eye. So they're macroscopic objects which behave as a single quantum object. On the other hand, in your laptop you have that process of 15 to 20 electrons, so a very small number actually, behave classically, and well, these transistors and all that's going on there. So it's not just size that can be the main thing about this, but it's very unclear actually. The border between the quantum and the classical world, if there is something like this, is being pushed very much by experiments. There are dozens of experiments with C60 buckyballs, so big molecules, Anyway, you have to make a cut in this interpretation somewhere. And it's hard to say on this one.
Something that's always bothered me about
Yes.
you're going to take your macroscopic system, your lab equipment, and you're going to say it's classical. But it's made out of atoms, right?
Yes.
It's just nothing but a whole lot of atoms interacting.
Yes.
That's what we believe. And each atom is quantum mechanical.
Yeah.
So then you have to be able to take quantum matter and glom it together and say in certain circumstances it's classical. I mean,
Yeah.
there can't, I mean,
But that's exactly the point. That's a problem. I mean, maybe I shouldn't talk about problems at this point because I'm just referring to Bohr, what he says and he thinks. But in this interpretation, you must at some point say, okay, this apparatus I treat as a classical system. What the justification for this is the question. There's a problem, I see. A problem there. Two, what you just have to do it to make the Copenhagen interpretation work. Okay, then the quantum mechanical formalism does not provide physicists with a pictorial representation. The psi function does not, as Schrödinger had hoped, represent a new kind of reality. Instead, as Born suggested, the square of the absolute value of the psi function expresses a probability amplitude from the outcome of the measurement. Due to the fact that the wave equation involves an imaginary quantity, this equation can have only a symbolic character. But the formalism may be used to predict the outcome of the measurements that establish the conditions under which concepts like position, momentum, time, and energy apply to the phenomenon. Okay, this is basically what I said before. The description of these classical concepts to the phenomena of measurements rely on the experimental context of the phenomena, so that the entire setup provides us with the defining conditions for the application of kinematic and dynamic concepts in the domain of quantum physics. Finally, such phenomena are complementary in the sense that their manifestations depend on mutually exclusive measurements, but that the information gained through these various experiments exhausts all possible objective knowledge of the object. There's this keyword complementarity, and you could also say this is kind of doctrine of classical concepts that's sometimes called. So what's this about complementarity? And this is where the famous uncertainty principle comes into the game, which actually goes back to Heisenberg, which was endorsed very much by Bohr. And this is really at the heart of the story. So let psi be a state of a quantum system, and a quantum system which actually has position and momentum. So we, all the time we talk about such a system, qubit would not have position and momentum, but let's say some kind of particle. And the so-called standard deviation of P, where P actually is the operator representing momentum, in the state psi is the following. Well, okay, I should explain this notation, these brackets. This is the expectation value. So this is just something very simple. So you take the expectation value of P squared minus the square of the expectation value of P, and the square root of this you call the standard deviation. And analogously you can define the standard deviation of Q, where Q is the operator representing position. And then the uncertainty principle states that for all states psi, the product of these uncertainties or standard deviations is at least 1/2 h bar.
Andreas?
Yeah.
If you just had the assumption of a Hilbert space, then what is P and Q? Don't you need to make further assumptions about the structure of the Hilbert space?
Yes.
Oh, okay.
This is why I said this. I'll show a more general form of this next. Actually, this applies to situations where, well, you actually need an infinite dimensional Hilbert space, then you can define something like position and momentum. But more generally, there is a formula of this form, which looks more complicated, but here A and B are two arbitrary self-adjoint operators on the Hilbert space. Then you have this more complicated formula about the product there, well, actually the squares of their standard deviations, is greater than 1/4 of the square of. Does this make sense? This doesn't make much sense. This page. Sorry. Here's something missing. Square brackets are missing. This is the commutator here. So,
you don't have Planck's constant occurring in there anyway.
You said it equal to 1.
You don't need it to, because that comes from...
Well, this is a standard trick. Physicists always say h bar is 1. It's natural units, atomic units.
I'm sorry, but aren't those expectations on
you
the
shouldn't
secondary
have things
response
Yeah, it should be.
operators?
It's a mathematical result then.
I'm sorry,
Yes, this
this inside there, the A thing bracket, that's a number, right? It's acting like a number. Am I correct?
This,
Yeah. That's
Yes.
a number, right?
yeah, this is actually
But you see,
number times the identity.
but that commutes with everything. So it passes out of the bracket.
This is the anti-commutator. This is not.
Oh, that's the anti-commutator.
I have to explain. This is the anti-commutator.
Oh, okay, sorry.
Okay, sorry. There's something missing here. I first want to explain that this doesn't make sense. What I wanted to write here is this expression. So it's the expectation value of the commutator, and the commutator, so the square brackets, which are actually missing. This is this expression, A, B, minus A. So the commutator measures how much do these operators, actually it's I times this thing. The commutator measures how much do A and B fail to commute.
That's where Planck's constant comes from.
Yes, here you usually have H bar, but it's 1. So yes, it's a good observation. And, as a physicist, you don't see this, but at some point H bar is 1.
No, because P is defined, the H bar enters through P, because P is minus H bar d by dx. So at this bottom level, there isn't an H bar.
Yeah. You can say it more simply, because the commutator of P and Q is IH bar. You define
But the H bar is entered in your definition
if you
of
like.
P. So
Yes.
there's no mystery about the H bar.
No, but H bar hasn't been set to 1 in that equation. There is no H bar in that
There's no H bar.
equation.
Yes. Okay. You're of course right. I mean, this more general formula should apply to P and Q also.
Yeah.
And then, of course, I would have to think about H bar. Is it actually something, or is it just 1 in brackets? But of course, this is wrong. So this is missing here. Sorry, I forgot that. So this is so-called commutator. This is an anti-commutator of these two operators. The anti-commutator, of course, just has the plus there, but no I here. Okay. We will not bother with this in any detail. It's just about the following. It is a certain limit to, well, how well can you know, let's say, position? Well, if you know position very, very well, so make this standard deviation very, very small, then know very little about momentum, because you have to have that the product is at least of this size, and the other way around. And this would be an example of P and Q of so-called complementary observables. So if you know one, you can't know the other. For Bohr and Heisenberg, this became really an absolutely central aspect of the whole story. This is a matter of principle, if you like. There are many interesting questions in that, and one question is if the uncertainty principle gives you an epistemological constraint on you, which, well, is due to unavoidable disturbances during measurement, or it's actually an ontological principle which says, okay, reality is this or that way. So the question is it actually constraining the nature of reality itself, independent of measurements or not? And it's not very clear, even with these long statements from Bohr that I had, what he thought about that. I found this, somebody said that Bohr was what we call an entity realist, possibly. So he thought that atoms are real things, but he was not a theory realist. So the theory was not supposed to actually give you a realist description of what's going on, a literal, pictorial description of what's going on. Rather, he had this elaborate tower of concepts that I talked about. So he thought that quantum mechanics gives you a symbolic description of the quantum world, and in particular the use of imaginary numbers, because we live in complex civil spaces, points to this. And complementarity he saw as similar in spirit to relativity, actually. He said both create a kind of contextuality for observations, relativity due to the existence of a maximal speed, and quantum theory due to the existence of a minimal action. Okay. Heisenberg was much more of a positivist, and I call this like degrees of instrumentalism. So Heisenberg was even more instrumentalist, and Kuhn is just giving you a calculational device to make some calculate the outcomes of experiments. And he was very influential with this, that it is meaningless to speak of the value of a physical quantity before a measurement is made. So don't even think about this. There are things in Heisenberg you read when you have a source here, a particle comes out, you have a screen here where it's detected, which basically is a position measurement, and so you must not think that the particle takes some kind of trajectory from here to here. It doesn't make sense to speak about that. That's how radical this actually is. So quantum theory does not tell you how the quantum world is, and in particular, if you don't have measurement, there's not much left of this. Okay. Well, this was very influential, and actually the expression Copenhagen interpretation is from Heisenberg, and some say he co-opted Bohr. He had somewhat different views on many things. Okay, this is what we call the Copenhagen interpretation. I took quite a lot of time to explain this, because this is the standard interpretation of quantum theory, and it is as strange as this. There was a lot of discussion on that, and one is the measurement problem. So I have to say something about that. There's this nice quote from Albert, who's a philosopher of science, and from his book Quantum Mechanics and Experience. The dynamics and the possibility of collapse are flatly in contradiction with another. The possibility of collapse seems to be right about what happens when we make measurements, and the dynamics seems to be bizarrely wrong about what happens when we make measurements, yet the dynamics seems to be right about what happens whenever we aren't making measurements. So what does it mean that? We saw quite a lot of this, but here's the famous Schrödinger equation. You must see the Schrödinger equation also. The dynamics of quantum mechanics is linear. It's given by this linear differential equation. So the state vector psi, which now depends on some coordinates r and on time, changes in time according to this. And, well, h hat here is the so-called Hamiltonian. This is the operator representing the physical quantity energy. Okay. So what does this mean in particular? Assume that we have some physical quantity A, such that the eigenstates of the operator A representing this form a basis, phi I A, of Hilbert space. One would assume that for t equals 0, the state of psi R0 is an eigenstate of A, so it's one of these phi i's. After some time t, the state will have evolved to, well, some kind of convex combination of these, or linear combination, I should say, of these eigenstates of A. And of course, in general, this is not an eigenstate anymore. Rather, psi RT is a so-called superposition of eigenstates of A. And we had this for spins, where states which do not lie in the direction where I measured, they're all the superpositions. Okay. So, of course, the dynamics can take me from an eigenstate to a superposition of states. This is very nice, and it really describes what we see in quantum theory, and this is very successfully describing microphysics when no measurement is made. But when a measurement happens, this is not described by the Schrödinger equation. Instead, we have the so-called projection postulate, which we already saw. This goes back to von Neumann, at least the name projection postulate. Physical quantity A is measured, and the result is, well, this value AI in the spectrum of A. And this actually happens with probability Ci squared according to the Born rule. This is.
What do you mean by discontinuous in that last slide?
Well, this obviously is a continuous change in time. So if you actually look how psi...
Yeah, okay, I see what you mean by that being continuous.
Okay.
But I mean, the other thing, the experiment takes a certain minimum length of time.
Oh, okay. Yes, I don't go there to describe measurement in mathematical terms. I refer to the projection postulate, which says, okay, in the instance of measurement, where measurement, well, not even Formalism is very clear about that. Who made this theory? He said, okay, it's the whole story with pointer states, but still, at some point in time, this projection happens. So the system jumps from a state it happens to be before measurement, or maybe during measurement when it has interacted with the measurement apparatus. It jumps into the eigenstate of that measurement outcome. I have assumed here that A is a non-degenerate operator and has the discrete spectrum, so it's this one instance where we use the simplest mathematical setting. This is why I say this change is discontinuous, because this is the famous quantum jump. You have some state which is a superposition, form a measurement, you get one outcome, AI1, then it's in the eigenstate corresponding to AI. Okay.
There are non-linear equations which model this very
Yes,
well. Design equations.
Yes, there's quite a lot of literature to describe the measurement process mathematically. But basically, let's say, a very simple, maybe cartoon form of quantum theory that I'm using here, it is actually this. You measure, and at some point in time, the thing collapses. This will collapse of the wave function, as it's called. And it's an instantaneous thing. At one moment you have a superposition, and a moment later you have just one of these things picked out by the measurement. What we do not, well, we do not see superpositions of macroscopic objects. Of course, we have to explain this. And many people see the measurement problem as the question: how does the macroscopic world in which physical objects have definite properties basically behave like classical physics tells us? How does the macroscopic world arise, at least approximately, from the microscopic world where quantum theory with its indeterminism holds? Okay, this is one way to look at the measurement problem. Another aspect is the question: what is a measurement? I'm talking about this all the time. With which physical interactions are measurements and which are not? I think this is one conversation that I like very much. Nobody can tell you what is a measurement and what not. That's very important to understand. No, it's true. I mean, okay, but this is the deepest problem in the foundations of quantum theory, so I don't have an answer. Okay. What should have become clear is that the status of the measurement problem depends very much on the status one ascribes to the state psi. If you see psi as a state of knowledge, or as a symbolic device, or as actually describing reality, it makes a difference for this problem. And more generally, potential solutions to the measurement problem, what would count as a solution, depends on one's philosophical and metaphysical position with respect to quantum theory and to physical theories in general. This will become clear from the next topic, and this is this famous paper by Einstein, Podolsky, and Rosen. And it's called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" It's from 1945. It's only 4 pages long. It's well worth reading. It's one of the most cited papers in the history of physics. It's kind of a point of culmination in the Bohr-Einstein debate. And of course, you all know that Einstein was opposing Bohr and Heisenberg, and he never was very happy with quantum theory. And this paper discusses the completeness of quantum theory. And, we also say the condition of completeness for physical theory is the following: every element of the physical reality must have a counterpart in the physical theory. Okay, sounds very plausible. And what is physical reality? Well, EPR don't claim that they can define physical reality once and for all, but they say there's the following sufficient but not necessary criterion for identifying physical reality. If, without in any way disturbing the system, we can predict with certainty that is with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So what you would say, if you see this, you say, okay. So what's the argument then? According to eigenvector eigenvalue link, the physical quantity A has a definite value A in a given state psi if, well, psi is an eigenstate of A via eigenvalue A. Hence there is an element of physical reality according to EPR corresponding to the physical quantity if the system is in such an eigenstate. If on the other hand we consider another physical quantity B such that psi is not an eigenstate of B, then B has no definite value in the state psi. There can be different outcomes of measurements with these different probabilities. And EPR conclude that such a physical quantity has no physical reality in the state psi. It's just according to their reality of, to their criterion of reality. And then they say that either the quantum mechanical description of reality given by the wave function is not complete, or when the operators corresponding to two physical quantities do not commute, the two quantities cannot have simultaneous reality. Well, I should say that this is actually, the latter statement is somewhat imprecise. You can have non-commuting operators which do have common eigenvectors. But there are pairs of operators like position of momentum or spin x and spin z, which just means measuring spin in the x direction, measuring spin in the z direction, which have no common eigenvectors. And this is actually what we will concentrate on, and what they do concentrate on. Okay. And then they consider an entangled state. They don't talk about entanglement actually. It is an entangled state of a composite system S. They write it in this symbolic notation. So they have one subsystem S1, one subsystem S2. They form a composite system S. And they suppose that the components S1, S2, they interacted sometime in the past, but they do not interact anymore. You can think of a spatially separated pair of electrons. This is actually what Bell did later on. They're not using this example, but this is it's okay to think about this. So now let A and B denote two physical quantities returning to the first component. So these are physical quantities of S1. Moreover, the state of the composite system can be written in two ways then. If I have an eigenbasis of A, just here it's UI. S1 is not a variable, just you could have written this as an index. Just means of system S1. Let's have this eigenbasis AI. Actually, the eigenbasis are not important. Well, okay. And that Bj being the eigenbasis of B. And I, of course, can write the state in these two different ways. So this is what belongs to system 1, and this is what belongs to system 2. The tensor product, well, this decomposition is not unique. I can either use this basis or another basis.
Wouldn't be dimension the same? You have to do NAM. It's.
Yes. Well, okay. Yes, it's an eigenbasis, and n would be equal to n. Yes, that's true. Now we suppose we perform a measurement of the physical quantity A on S1. So this is really electron 1 sitting here. We don't fiddle with electron 2 over here. Let's assume we obtain the value AK as our measurement result, and the state of the composite system changes from this state we had here to this one. Just pick out the kth component, if you like. This means that the second component, the second electron over here, S2, is left in the state psi k for S2 after this measurement. Okay. If you are saying you could also perform measurement of B on this electron over here and obtain some PL, and the state would change to this. So in this case, S2 is left in the state phi L. S2 after measurement. Okay. It now can happen Okay, now let me say this first. EPR argue the following. Despite the fact that S2 is left in two different states after the measurements of these different quantities A and B on S1, no real change can take place in S2, just because S1 and S2 do not interact anymore. So this also sounds very plausible. I mean, I measure over here, and then I don't do anything with S2. Let's say, thus it is possible to assign two different wave functions to the same reality. The second system after the interaction with the first. Reality here refers to reality what was the case with the second system. Okay. Now it can happen that the two states of system S2 are eigenstates of physical quantities C and D, which belong to the second system, such that the operators representing these physical quantities have no common eigenvectors at all. I'll show this in an example involving position and momentum of S2, but it can also be done for spin in X and spin in Z direction, for example. Okay. But eigenstates allow to predict the outcomes of measurements with certainty. If I know that the system is an eigenstate, then I know that the physical quantity has the eigenvalue corresponding to this eigenstate as its value. Okay, so we are forced to ascribe reality to both physical quantities C and D, despite the fact that they have no common eigenvectors. This is something that quantum theory would not allow you to do. So EPR conclude the quantum mechanical description of reality by the wave function is not complete. And this is a pretty strong argument, and I found it in this paper. I'll come to the paper later on by Greenberger, Horn, and Seilinger, and they say in 1985 this EPR paper had 49 citations, so it's 50 years after it was written. So it's discussed a lot, and it's a very strong argument actually. Which,
but is it 49 citations?
49 citations in the year 85 alone, so 50 years after this was written. So, some remarks on that. There is this, you may feel a little uneasy about this notion of elements of reality, and it sounds a little stranger. It is not really the heart of the argument. If you think about it, it's really a question of if quantum theory is correct, then doing something over here to system S1 can actually have an effect over here. And it is also it's also stronger than saying, well, if I now measure on system S2, I'll find this and that. It's actually saying, if quantum theory is correct and the further assumptions are correct that we made, there are some further assumptions which are important in this, then I know with certainty that upon measurement I found this and that value for position and momentum, or for spin in X and spin in Z direction. You can continue the argument, you can basically fix the value of every physical quantity of system S2. And since the quantum mechanical formalism does allow me to predict the values of these physical quantities with certainty, the formalism cannot be complete. So there's this elements of reality which sounds a little strange. It really only enters in this last step of the argument when you want to say, okay, quantum mechanical description of reality, and then you have to say something, what is reality? But it's not at the heart of the argument. So what is at the heart of the argument, and this is very different from Bohr, is it is an ontological argument in the sense that physical theories are supposed to describe or mirror an underlying reality which is independent of the observer measurements. Something like that. This is a very important aspect. If you read the reply that Bohr wrote to this paper, which is not very easy to read, but well, just sit down. It's also not a long paper. You'll see that he just doesn't accept the notion of reality supposed in this. So this is really where the heart of the difference is. I also want to emphasize that there's no argument here about signals, speed of light, nothing about relativity. It's not about that. Later on it will be interpreted respect to all these things. It's just not there. How does space-time picture enter at all? This is not even mentioning of space-time in the paper. It is entering in the following sense. If you talk about non-interacting components or subsystems, then it's mostly interpreted as a spatial separation between the systems. And this is where this famous concept, this is actually the additional concept that they put in here, the local realism. This is where this enters. What does local realism mean? Well, it's one of the last quotes I'll actually bore you with. But this is Einstein himself saying what local realism is. He says, probably one supposition we should, in my opinion, hold absolutely fast. The real factual situation of the system S2 is independent of what is done with the system S1, which is spatially separated from the former. So EPR point out a certain clash between local realism and quantum theory. That's what this is about. And Einstein didn't want to give up on local realism, but as we see, nature doesn't behave that way. Well, what happened then, what I'll skip mostly, is people started to develop so-called hidden variable models. Lots of them. They said, okay, if the description is not complete, there may be additional parameters, hidden variables. This is, well, things beside the state vector, which then actually can restore causality and locality to the theory. A lot was tried, and then in 1964 this paper came. John Bell actually, of course he did a lot in the foundations, but he actually was at CERN, and he's a high-energy physicist, so also was kind of an outsider, but he has a very, very healthy influence on the whole story. He wrote this very famous paper, which is also very short, and he showed that local hidden variable models cannot reproduce the equations of quantum mechanics. So this is one of the famous no-go theorems. Well, Bob tends to say that you can't learn much from things that don't work, but still it was very important for the discussion. And I'll tell you what you can learn here. Actually, this should be the minus. I'm sorry for that. Yeah. This is this Bell state we saw earlier on, and I think you called it the EPR state.
Yeah.
Okay, anyway.
Because you say consider an EPR situation.
Yeah. That's, I don't call it the Bell state. So, okay, it's... Well, for you it was the... Yes, you're right. Yeah. Okay. Anyway, you consider the EPR situation with two electrons in what is called the singlet state, and except for the minus here, it's actually what I've written down. What does this mean? Well, you have these two components, and this is symbolic notation. This is arrow up and arrow down. Just fix some direction in space and make a spin measurement in that direction. Well, then this observable spin in this direction has two eigenstates. The up state is one eigenstate, the down state is the other one. And you say, okay, if I choose another direction, will the state change? No, actually, you can see quite easily that this state is not dependent on which direction space you choose, so I didn't have to be explicit about which direction. It's rotationally invariant. The total spin of the composite system is 0, so that's called the singlet state in physics. And moreover, it's also important, and it's usually not mentioned at all, only the spin degrees of freedom of the system are shown in this wave function. Of course, we want to think about two particles which we can take apart, though they do have spatial degrees of freedom. They don't show up in this wave function, we just concentrate on the spin part. Okay. So what's the idea then? We assume that the two electrons are spatially separated and do not interact. Quantum mechanics then predicts that if we measure the spin of the first electron, which I again call S1 in some direction A, and several things happen. First of all, the result is either 1 or minus 1, and this is also every spin measurement. Secondly, if I measure the spin of the second electron, S2, in some potentially different direction, B, then I get a correlation between the measurement results. So I assume that A and B are unit vectors, and then I just want to know the expectation value of this operator, which means measure electron 1 in direction A and measure electron 2 in direction B. Then, well, you get the expectation value of this operator is minus the scalar product of A and B. So what does this mean? In particular, if B equals A, you obtain what's called a perfect anti-correlation. Namely, the measurement result in S2 is the negative of the measurement result in S1. Remember, both results are either -1 or +1. So this is what quantum theory tells you. Why is that? Well, if you look at the state, again, it's quite clear. It's basically picking out if I measure this on the first system, and I'll measure this on the second, and way around, if I measure this on the first, and I measure this on the others. Okay. So this is not very surprising. This is just what quantum theory tells us. So the question is, can I find a theory which is local and gives me the same thing? Well, what does this mean? Well, assume that the result, and I denote it as S1 of A lambda of the spin measurement S1 additionally depends on some so-called hidden variables. Lambda, I should maybe not have written additionally. The lambda includes the state vector psi, but there can have additional parameters. And there's no limit on how many you want to have. Just say that there is some theory doing this. Likewise, the result of the spin measurement on S2 depends on these additional parameters. Then the main assumption of local realism is just that the result of the measurement on electron 1 does not depend on B, which is the direction in which I perform the measurement on 2. And likewise, as the measurement result on electron 2 does not depend on A. Okay. So, well, this is, we need a little more explanation actually. I assume that these so-called hidden variables lambda have a probability distribution, and actually I just want to look at those hypothetical values of lambda which give me perfect anti-correlation, which I expect from quantum theory. Then the expectation value of the product of the outcomes, and I'm not quite sure if this actually is the right version. I saw that this is called a quantum correlation, but this actually is a classical correlation, if you like. This is a classical one. Anyway, it's a correlation anyway, so I'll check. I saw this. What was this? Well, it's given by the following. You integrate over these hidden variables. Actually, you would integrate just over the set of lambda such that you get a perfect anti-correlation for A equals B. And you get this thing. And then Bell shows that this cannot reproduce the quantum mechanic expectation value minus a scalar parameter V, not even approximately. And Bell is very cautious, but he tends to the conclusion that the clash between quantum mechanics and local realism is the latter. Namely, local realism, that must go. Okay, actually the argument is not very long, so have a look.
He writes that because I've heard that he actually was a local realist. The whole point of this was just...
I don't know that. So if I read the paper actually, and he is not very... Well, the thing is, there were no experiments at the time, so he doesn't commit himself too much. I read it more in this way, but I don't want to overdo this. The interesting thing is that Bell derives a certain inequality between the quantum correlations in his proof, and roughly this inequality gives you an upper bound to the amount of correlation that can be obtained from local hidden variable theories. But quantum theory gives you stronger correlations than this. So this opened up the road to experiments, and that's very interesting. Any experimental violation of this inequality by Bell proves that the local hidden variable theories cannot reproduce predictions of quantum theory. At the time you could say, okay, this I just don't know. Namely, in the 60s, when this was written, no such experiment existed. The reason was the following. Well, you had to set up your detectors for your measurements of the spin directions well before the experiment started. Then you could always argue, well, the detectors could interact in some way. This could produce correlations. There could be some kind of communication taking place. And since we ultimately would have to describe the whole thing as a quantum, well, there was a lot of arguments. what you would have to do is, well, you produce these particles, they fly away, and then while they are flying, you have to adjust the detectors. Obviously, you have to be very quick to do that, and it was done in 1982, 1981, 1982, on that aspect. Did some experiments to that effect using photons, and time varying analyzers is in the title of this paper. And I say here they are widely regarded as proving violations of Bell's inequality. Widely regarded means there are many people who disagree also, but by now there are many different experiments all pointing in the same direction, so there's a lot of literature on so-called loopholes in detector efficiencies and whatnot, but basically it's proven. So if you like, have a look at that, but I wouldn't waste too much time on that. I don't know.
If you're lonely, you have to go and talk to one of those guys.
Yeah.
They can keep you busy for a couple of months.
Yeah. Yes, that's true. So from these experiments, quantum theory is confirmed while local realism is refuted. And, well, it's quite a strong statement. But original inequality is rarely used. The related inequality is the Clauser-Horn-Shimoni-Holt inequality, which is this one. A and A prime spin directions measured on S1 and PP prime spin directions measured on S2. Just wanted to show this. This is it's a little more beautiful than Bell's original inequality. Okay. Further development in that direction are the so-called GHZ states and Bell's theorem without inequalities. And this is actually the most recent paper I want to talk about, so I'm not as up to date as this book of 2007 or things like this. A paper from '89 by Greenberger, Horn, and Seilinger, and well, they made the following observation: that first of all, the EPR argument applied to spin measurements uses the case of perfect anticorrelation. I was talking about this a lot. So spin measurements in the same direction of both particles, while Bell needed to consider spin measurements in different directions in order for his argument on correlations to work. Okay. In fact, there exists a classical hidden variable model for the case of perfect anticorrelation. So GHZ considered this is also true beyond the two-particle case considered by Bell. And we can the case of perfect quantum theoretic anticorrelation always be modeled by a classical hidden variables model. So this is a much more limited question than asking is there a classical hidden variables model reproducing all of quantum theory. It's just about this one case that actually is important in the EPR argument. But it turns out that for a pretty simple four-particle state generated from a Bell-type situation, the further decay of these two components, there cannot be a hidden variables model to reproduce the case of perfect anticorrelation. So it goes wrong. Can't do this. And soon after, similar arguments were made for three entangled particles, and this is what started different things. First of all, they also suggested experiments, and these experiments were done by now, and they confirmed these theoretical predictions. They also started the business of multipartite entanglement, which is very important in quantum information theory nowadays. Okay. Yeah, one of my favorite theorems actually is the theorem by Gleason, and this concerns the probabilistic aspects of quantum theory, if you like. And this is from 1957, and if you just want to read one of all these papers that I mentioned, then read this one. It's very ingenious proof, actually. And, we saw the spectral theorem already, and I want to do very, very little of quantum logic, but I will say a few words about the following. Namely, a proposition of the form A is a delta, which means the physical quantity A has a value in the set delta, that is, of course, a subset of the reals. This corresponds to a projection operator P, sometimes symbolically written this way also. If the algebra of physical quantities that we have, so now I'm just thinking some operator element at this point, but you can always think of all bounded operators in infinite space. But holds more generally. If the algebra of physical quantities is a phenomenal algebra that contains, of course, this operator you want to talk about, then also this projection P is contained in the algebra. Actually, all these projections that can generate for different deltas are all phenomenal. So if we now take the probabilistic interpretation and aspects of quantum theory seriously, we have following two questions. First of all, what are the minimum requirements for a mapping from the projections, which represent propositions, the unit interval, to count as a probability measure? The second question is, how do these measures relate to quantum states? And these are exactly the questions that Gleason treated in his paper. First of all, the projections on a Hilbert space, more generally projections in phenomenal algebra, form a complete lattice. The lattice operation is actually easy to understand for the isomorphic lattice of closed subspaces of Hilbert space. Every projection projects onto a closed subspace. So if I have two projections P and Q, and I have the corresponding closed subspaces UP and UQ. But P is smaller than Q, of course, just when UP is contained in UQ. And then I define the mean or the minimum of P and Q is the projection corresponding to the intersection of these two closed subspaces. The join or maximum corresponds to the closure of the subspace generated from the union of the closed subspaces. Two projections P and Q are orthogonal if the subspaces just intersect trivially in the null subspace. And in this case, I have that the product of P and Q is the same as, well, PQ is QP is just a zero projection. Over the lattice P of H, or more generally, P of H is the projections here on Hilbert space, on Pn is the projections in phenomenal algebra. These are all the complemented lattices for just sending P to 1 minus P. On the level of subspaces, you go from one subspace to orthogonal complement. And clearly, P times Q equals 0 if and only if P is smaller than or equal to 1 minus Q. Okay. What about probability measures? Well, first of all, the identity operator 1, of course, represents the trivial true proposition. The probability measure of the projections would be mapping mu from the projections to 0, 1, such that, well, first of all, I send the identity to 1, and then if I have P and Q being orthogonal, then the mu of P or Q is just mu of P plus Q. This is required to be mu of P plus mu of Q. This actually, you would probably agree, are actually the minimum requirements for this to be called a probability measure on projections. More specifically, this defines a finitely additive probability measure if mu behaves additively on countable families of pairwise orthogonal projections, and mu is called countably additive. Okay. Well, the task actually that Gleason set out to solve was characterize these probability measures for H, at least three-dimensional Hilbert space. We showed that if Hilbert space is at least three-dimensional, then every countably additive probability measure of projections is of the following form. Well, mu of P is trace rho P, where rho is a density operator. We'll have to define what this is in the next slide. Okay, but those of you who know quantum theory will of course recognize rho. The density operator rho is a positive trace class operator of trace 1, and it induces a linear functional on B of H from some non-algebra n of norm 1 that is a state in a mathematical sense by the following thing. Well, trace rho goes from B of H to C, it sends an operator A to trace rho of A. States of this form are called normal, and these are exactly the ones that behave additively on countable families of projections. It means if I have a countable family of pairwise orthogonal projections, the trace rho of the join over the whole family is the sum over the traces of the elements in the family.
Sorry, Andreas.
Yeah.
What was B and H again?
B and H, okay. This is the standard notation for all bounded operators in Hilbert space. Sometimes you find the notation L of H also. B of H is pretty small. Okay, normal states, or just the identity matrices, are usually regarded as physical states. They are more general than these states psi we were talking about all the time. And they are what's called mixed states. They generalize the vector states psi. And the vector state, as we saw, is just this thing. Psi, here's the slot of psi. And normal states are best seen as convex combinations of vector states. That's what we know. Okay. So, one more thing. If I have a normal state, trace row, and restrict it to the projections, I clearly get a countably additive probability measure. So Gleason's theorem shows that there is a projection between normal states and countably additive measures. And this actually justifies that we calculate expectation values using the trace, which, well, Gleason was 1957 and this was suggested in 1928 by von Neumann. I would say Gleason's theorem is very important in the following perspective. We talk about quantum theory being a probabilistic theory all the while, but he really figured out what are the minimum requirements for a theory to be called a probabilistic theory. What is the minimum requirement for something to be a probability measure? And then he showed, okay, this exactly corresponds to what we did in quantum theory all the time, namely using quantum states for calculating these probabilities.
So it's worth saying that there is a pure state version of it.
Yeah.
So you just add one, and that actually is the whole core of the proof to get that right.
Yeah.
This
okay.
Born rule is the unique probability you can define such that, so you have an additional requirement then that, so you said that on one it should be 1, and I think that there should exist a state on which it is 0 too.
Okay.
I think, and then you get the pure state version now.
Okay,
And the core of the proof is really establishing that.
Okay. Well, let's show me this. Done like this. Okay. Just as a remark, there are phenomenon algebras and also such of physical significance which do not possess any normal states. And remarkably, Gleason's theorem can be generalized. And it's the following: let n be a phenomenon algebra with no direct sums of type 1, 2. This actually corresponds to this two-dimensional Hilbert spaces which we are.
But for mixed states, you have a lot of ways to calculate probability.
No, only one.
That's you say for pure state.
For pure state there is only one.
Yeah,
and
for
the mixed state follows from that. So
okay.
it's just
So
mixing.
you must really have a look at this.
Yeah. So pure state you can show that the Born rule is the only one where you've got this mutually orthogonal summation. It's the only one. So it's not a random rule at all.
And so if we have such a phenomenon algebra, then every finitely additive probability measure of PNN, it's really about finitely additive because it's really pretty weak. What you presuppose here can be extended to a state of n. And this took more than 30 years to prove. So this is a difficult beast. There's a very nice paper by Maeda who gives an overview of the whole development. It gives a very clean.
This is different than something like teleportation because people were looking for it.
Yeah.
Just didn't come.
Yeah,
just couldn't get it
People were
right.
looking for this for a long time. Yeah.
Sorry,
And I
when
want to
you say countably additive measure, does that sort of imply that P of H, so the collection of projections, is a sigma algebra for some topology?
Yes, this is when I said it's a complete lattice, which actually means I can take the maximum arbitrary families and also the minimum arbitrary families projections. Yeah, it's not just a sigma algebra; it's even more.
Okay.
So, for the lattice,
When you say measure, is that in the ordinary sort of integration theory sense of the word?
no, it's in the sense that is defined here. Measure,
Okay, so it's separate from.
yes, it's exactly this kind of mapping.
Yeah.
This is what it's called.
No, fine. No, yeah, I can see the definition. I was just wondering what I was trying to associate it with a normal integration theory measure. And I just wanted to be clear it's distinct concepts or the same concept.
The best analogy is that if you take a measure in the normal sense, you take the measurable subsets as an arbitrary closed set. And you consider the null sets as an ideal in sitting inside this algebra. They mod out, take the algebra of measurables, modulo the ideal of the null sets. And most of the time that will actually give you a complete Boolean algebra. And of course, and then the measure is well defined on this because all you've done, you've modded out by the null sets, and so each equivalence class has unique measure assigned to it. And actually, this is a sort of a hidden hypothesis that's in much of integration theory that a measure space is called localizable. If this is true, that the measurables modulo the null sets form a complete Boolean algebra. In particular, it is the case that every sigma finite measure space is localizable, and most of the classical theorems about sigma finite measure spaces generalize to localizable spaces. So, for example, when you build a Neumann algebra out of a measure space, that measure space has to be localizable. This is something that's often somehow swept under the carpet. If you do L infinity of a completely arbitrary measure space, then that needn't be a von Neumann algebra.
I want to emphasize one thing, why this theorem is so strong, actually, why it's surprising. If you look at this condition here, this is condition on commuting projections. Well, this is pretty clear. This is a strong condition, obviously, but that's the only condition you have there. And you could say, okay, I do have a non-distributed lattice of projections, but Lee's theorem just gives me conditions within the distributive sublattices, because this is condition on commuting projections which lie in one distributive sublattice. But in the end, you see that you get the state of the whole non-commutative algebra. And of course, this behaves linearly on all operators. And this is why this is such a strong theorem. This is why this is surprising. Why does this happen? Well, it happens because every projection operator, let's say P here, of course, it has conditions with Q, which they lie in one context. But P lies in many different contexts. So in this indirect way, you're not free to do what you want with P in another context because it has some conditions over here. It's the same P and lies in different contexts. So in this indirect way, you do get conditions across contexts. And this is where the power of this comes from. So it's really a strong theorem, and especially in generalization is strong. The proof of generalization very much relies on the original theorem. So still lots of ideas were needed.
Although it's valid for infinite dimension, the essence lies already in 3 dimensions.
Yes.
The whole proof takes place on the 3-dimensional case.
Yes.
So you don't even have to talk about sigma additivity in principle. It's just to lift it. So it's just all binary additivity.
It's actually true. Yeah. Okay. The final thing I want to discuss in a few minutes is Koch-Schwecker theorem. This is 1967. It's also about hidden variables. Or I should rather say it's about hidden states. So it's pointing in another direction than Bell. And it's about the following. Bell considers local hidden variable theory, so it's about locality very much in relation to space-time. Koch-Schwecker asks a different question. I mean, can there exist a theory underlying quantum theory such that the state space picture, similar to classical physics, can be regained? And an analogy would be, statistical mechanics is underlying thermodynamics. And if you understand statistical mechanics, you actually get a state space picture. And you can see that all the physical properties of thermodynamics, they arise from this underlying theory of statistical mechanics. So what do I mean with the state space picture? Very briefly, classical physics, physical quantities are represented by real-valued functions on the state space S of the system. The points of state space, of course, are just the states, and in any state S, all physical quantities have values. Well, okay, these functions representing the physical quantities are just evaluated at this point, and I get a real number. This is the value. And if a hidden state space, well, this is just again this notion of hidden basically means we don't know what it is. If a hidden state space theory, underlying quantum theory exists, then each self-adjoint operator should correspond to a suitable real-valued function of this state space omega. The points of this hypothetical state space would not be vector subside Hilbert space. I would emphasize this because we talked about state space for quantum theory. This is actually asking, is there a different mathematical formalism which is more fundamental? So state is really in this sense of something which assigns values to physical quantities. Okay, so let us assume that the self-adjoint operator A is represented by some function fa. So of course the self-adjoint operators that we know as physical quantities, they should show up among these functions. There might be more, but those we know should show up. This naturally requires two things. First of all, the range of the function fa should be the spectrum of the operator. The range of possible values is just the spectrum of the operator. And secondly, if I have some operator b given as a function of a, g of a, then I should have that the function representing b is of course the function g of a. This should be g after f of a. These look like very natural conditions, and this is of course how it would work in classical physics. And this g is actually something Steve, when he asked what would happen if I collapse. This is the kind of behavior you would expect, also for non-injective functions g. Okay, this is how it behaves in classical physics. Okay, now that omega be a point of this hypothetical state space, then we can evaluate the functions fa and so on all at this point, and so we get values. We go back from the functions to the operators. We would have a function which I denote v omega from the self-adjoint operators to the real numbers, such that we have these things in the positives just from these two properties. To every self-adjoint operator, I would assign some element in the spectrum. This is the value, and if I have some function which I can apply to a, right here, real-valued Borel functions, because this is the kind of functions you would use in phenomenal algebra like DFA. Then, well, the value of g of a should be g of the value of a. Think about a very simple function. If I have well, a squared, I would expect that the value of a squared is the square of the value of a. And such a function is called a valuation function. So if I had such a state space picture, I would get these valuation functions. So you have to check if they exist. So there exists as a necessary condition, since this one is set. Okay. We can make the argument simple. For every non-trivial projection P, we have that the spectrum is just 0 and 1. And since every self-adjoint operator is the limit of linear combinations of projection operators, this is again the spectral theorem, we can concentrate on projection operators for the whole thing. And this means the question for the existence of variation functions boils down to questions for the existence of two valued, 0, 1 valued, finitely additive probability measures on P of H. Okay, there's a little more to prove that we get a probability measure, but that's quite simple. Gordon Specker showed that if your Hilbert space is at least three-dimensional, then there exist no such measures on P of H. Hence, there are no valuation functions. And hence, there's no state space model of quantum theory. It just doesn't work. And a little more strongly, since these valuation functions do not exist, you cannot even think, as long as you accept that the self-adjoint operators in some phenomena like P of H describe the physical quantities in quantum theory. As long as you accept that, you can even think that they will have values at the same time. There are just no functions which would assign these values. And interestingly, Gordon Specker gave a finite configuration using 117 lines in Hilbert space, arrays in Hilbert space in 3 dimensions actually, and they show that basically you cannot assign zeros and ones to them in a consistent way.
Can you do it for the case of spin linear?
Yeah.
Yeah.
Yes.
I
think they do it in their paper even.
Yes, you can do it for spin one. Yes, they even do it in the paper. It's true. There is a hidden state space model for a single qubit, and Gordon Specker do it in the paper. That's true. Okay.
But you can't put them together for two qubits.
No, what?
No, for 2 qubits it's gone. It's 4-dimensional liquid space and then virtual. I dare to mention this small paper by myself, which gives a generalization to the non-algebras. The only things you have to exclude are type 1, 2, and type 1, 1, which would be the real algebras, where you have these things.
But what kind of function they count as functions? I imagine it's not all functions, not all.
Functions you can apply to the operators are Borel functions.
Borel.
Yes. Let's see
Borel
where
function.
we have this. This function G is a Borel function. This is, well, there's just theorems and algebras. If you apply Borel function from the reals, actually from the spectrum of A to the reals, to...
And Borel is like local integrable?
Yes,
what,
it's measurable functions.
Well, it's Borel measurable.
Borel measurable.
It is, for Neumann theory is very often called non-commutative measure theory. So this is the right class of functions to apply. Okay, physically, I just want to mention that going to other phenometers just means you can incorporate things like symmetries and or super selection rules, but still can't have a state space model. Okay, I think this really not that much. This and one more slide. We saw that the Cohen-Specker problem is the question there are evaluation functions, but equivalently the question there are two-valued measures of projections. Since every projection represents a proposition, actually, mapping from proposition to projections is not one-to-one, actually. One projection represents a whole number of propositions in general. Well, such a measure can be seen as a Boolean truth value assignment, because I interpret this as false, this as true. The Cohen-Specker theorem hence shows that we cannot assign true and false to all propositions of the form A less than delta at once. So it's just not possible to think that they all have a truth value. And I must mention, this is really the last thing I want to mention, many people interpret the Cohen-Specker theorem as saying that there are no non-contextual states models. And what does this mean? Well, contextuality comes in a certain variety of meanings. The context can be an experimental setup, it can be a collection of co-measurable physical quantities, which basically means they all commute as operators, or algebraically as a commutative subalgebra of the non-commutative, then usually C-star of a non-algebra of physical quantities of the system under constant direction. And the perspective of Cohen-Specker's non-contextual says they ask for variation functions which assign values directly to the self-adjoint operators without taking care in which context they lie. A contextual theory, in contrast, would allow the value assigned to some operator A to depend on the context considered. I must really admit that it's not very clear to me how much sense this would make. Some people like this kind of argument. If you read Bohr's view of quantum theory goes quite close to that, actually. He says you can either ask for a position or for a momentum. You cannot have both. Okay, that's it.
What's the status of the Cohen-Specker theorem for real quantum mechanics rather than complex quantum mechanics?
I want to check. I can check this in 2 minutes. I think that Cohen-Specker, the original counterexample was not in C3 but in R3. So it does hold.
Gleason's theorem is in R3.
Gleason's theorem
is in
well,
R3.
you can. I could also mention this. Cohen-Specker put some emphasis on the fact that they have this finite configuration, but you can quite easily use Gleason's theorem to prove the Cohen-Specker theorem. And you can use the generalization to prove the generalization of the Cohen-Specker theorem. And Gleason definitely works in 3 real dimensions.
That's where the core of the proof is. 3-dimensional real, that's Gleason, where it lives.
Right. So if you take like a complex numbers function instead of real functions, it change anything, you know? The proof.
Yeah, this will change a lot. Why did I take? I'll show you why I took. I mean, here, if I, for example, the thing is that I want to talk about self-adjoint operators. So I can only apply a function of this kind from the reals to the reals to get from a self-adjoint operator a self-adjoint operator.
You could
But
talk
what
about
you have
normal
to
operators
see-
instead, for example. You could talk about normal operators instead.
Yes,
It's
you
not
could,
clear what
but,
interpretation.
You could, I never thought about this in idea. Well, the thing is that physical motivations talk about physical quantities, which are represented by self-adjoint operators. Yeah.
But more generally, what do you think is kind of role of real numbers in this story? Because
There's not too, well, actually in this paper I have there, I consider functions from R to C and show that if you have this condition that the valuation commutes, as they say, the commutes, where is it? No, it's in the same slide, sorry. If you have this for self-adjoint operators, then you, it also implies this, and if you go functions from R to C. So this is not really important. You would, I would not know what to do if you want to start from operators which are not self-adjoint. The thing is, this of course is well defined. The thing is, this is a proof by contradiction. These things do not exist. So you want to presuppose as little as possible anyway, and then you don't want to. You can always say, okay, if I have a valuation function which behaves linearly in the following sense that valuation of say that every operator in the Formalism array can be decomposed into self-adjoint operators, as you know. So I can look at valuation functions of this kind. So this would be posing an extra condition, if you like. Actually, what I show, my proof I do the following. I say, okay, if we have valuation functions, then it's canonical to define an extension of the valuation function in this way. Then you go on, if you have this, to quite easily see that you get a state from this thing. And the state, again, has a property which, well, if you cannot have this property, you will not always map to the spectrum. And especially if you look for projections, you will not always get just 0 or 1, you will get values in between. And this means that you just can't have these valuation functions.
Does that mean that if you relax the condition that the valuation function lies in the spectrum, to lying in the numeric range, you actually remove, you then can't prove it?
So I didn't want to, where do you want it to lie?
So instead of the spectrum, you look at the numerical range of the operator, which is its convex hull
Yes.
of the spectrum.
Yeah, of course, yeah.
And would that be, would you still get a third as part of the spectrum results, or does it then not hold?
I don't think you would get it. Well, the whole argument is always based on the fact that to projections you can either assign 0 or 1.
Right.
Yeah. This is both the original proof and also my generalization is based on that. So if you remove this, then it's not obvious at all if you could still prove something like that.
If you added a maybe.
You can always add a maybe, but this is actually the question. Is there a way to write quantum theory without maybes? Is there a way to assign values or not?
Well,
the interesting thing about this, well, of course it is, Hilbert space is in here, but it's a very general question. Can I assign values to self-adjoint operators under these two conditions, which physically are very natural? And I would say this, also mathematically they are quite natural, but you can think of other things and then probably couldn't prove it. Physically these are natural conditions to look at.
But you mean you might physically want to know, can you definitely assign a maybe?
I might want to know.
maybe.
Maybe, yeah. Okay. Any further questions?
Could you say anything more about dimension 2 examples?
Dimension 2 is always special. This is interesting actually. It's special in Gleason's theorem, it's special in here.
You don't have subspaces which are non-trivial. That's
Exactly,
mainly
that's
the point.
That's the point. Yeah, I wanted to
You've
find
got no
this.
structure.
Yeah.
You've got a bag of states. Because all these things very much rely on the lattice structure. You don't really use a lot more than the lattice
Or
structure.
what about topological structure?
The topological structure is.
You extract it actually from the lattice structure. Like Gleason is purely a lattice theoretic theorem for, and this follows from Gleason.
You can wonder about topological structure and continuity and things like that.
Well, that's what Gleason does. He builds continuity from the lattice structure.
Yes.
In his
Yeah.
proof.
Yeah.
A spin 1/2 particle has a very peculiar property that every state is up in some direction or other.
Yeah.
You can always pick its polarization vector.
Yeah.
And so it's the eigenstate of that in some direction.
Yes.
And that's not true of any other system. That's just very peculiar to the spin 1/2 particle.
That's true, yeah.
So,
I'm thinking along the lines that Bob is mentioning. These are lattice theoretical conditions we have, and then for two-dimensional Hilbert spaces basically have no. I said that the whole power of Gleason's theory comes from the fact that the projection lies in many different contexts, and this is exactly what fails in two dimensions, because you have a single. Well, if you have a projection P to some one-dimensional subspace of two dimensions. Then there's exactly one context which contains this one. No other context contains it. And that's basically why you get no further conditions from this condition that Gleason has on P times Q equals 0. So all these conditions are vacuous, and then you're basically free to do whatever you like context by context. And this allows you to find these value assignments.
I think Abazettelas as a proof for Gleason, in which he basically goes through domain theory structure from the order, then builds a topology like that, which is something you would definitely appreciate, I guess.
Well, I was thinking more of manifolds, because I mean, you were drawing the sphere of states, which obviously has a Hausdorff topology, and you're identifying antiptable states, which is, I think once you identify the states, you're getting to the to the space of commutative subalgebras, which is the kind of thing Chris and Andreas are working on. And that too has its topology. So if you ask, in Chris's terms, if you're looking for global sections, if they have to be continuous, I think that gives you stronger conditions than maybe Gleason was proposing.
Continuity would give you, well, some kind of relations between projections. You would know when they are nearby or not. Yeah. You don't see this directly from the lattice structure, but as says, Gleason basically reconstructs this from
the lattice structure. And he really, because you see, he has these pictures in his paper where you really see the continuity reconstructed.
Only for the high dimensions.
3 dimensions. It does 3-dimensional real. So 3 dimensions are enough to have enough structure. That's the thing. So, but a lot of these structural theorem, like there is one structural theorem which only starts at dimension 4, and that's like Piron's theorem on which lattice theoretic actions you need to be able to reconstruct Hilbert space. And there you need 4-dimensional structure to be able to do that. A lot of these were very much in lattice theory tradition. So quantum logic was not just about interpretation, but it was sort of the formal machinery people were using to challenge these problems.
I'll ask a slightly different question. I mean, earlier in your lecture you were talking about the Copenhagen interpretation, and we discussed somehow about the notion of measurement being classical in the Copenhagen interpretation is sort of unsatisfactory if you think measuring systems made of atoms and so on. I'm just curious to know whether you would like to spend a couple of minutes telling me what, or something else, what you think, whether you think the measurement problem can be solved within standard quantum theory, or whether, you know, like you mentioned Penrose's book, for example, it means we need to go beyond quantum theory to come to a satisfactory resolution of the problem.
Okay. I hope it's interesting enough for the audience, because this is my speculation on this. And it is with all these very hard problems, so very clever people have been looking at for decades, and nothing definitely comes out. You wonder, is it a well-defined problem at all, or are we simply looking at the wrong thing, or trying to achieve something which is not achievable? I suppose that Einstein was quite right with his uneasiness about quantum theory, the lack of giving a realist description. And that's why I say this is my speculation, this is my point of view. You cannot be a naive realist, because nature, provably, experimentally shown, doesn't behave that way. But to take the consequence and say, okay, we cannot do better in principle than quantum theory, because quite strange apparatus of Copenhagen and this German denkful, which is, well, you are prohibited to think that a particle is flying from here to here. Everybody does that. Everybody thinks the particle flies from here to here, it's detected over here. But still, if you take the formalism seriously, you mustn't do that. So, all these things, some technical things, point to the fact for me that we have to change the formalism of quantum theory, and we have to change it trying to get at more realist theory. And this is very hard to do. And I think one thing you can do is, well, first of all, you can change the logic that you use to describe these things. And quantum logic is not very successful at doing it. There's another big program which has been running for decades and has not really produced good physical insight. The other thing you can change, and this seems at least plausible, is this: why do physical quantities always have real values? Yes, we do get pointing to some point in a measurement, but maybe we can change the formalism somewhat and allow for a little more leeway in this, and say, for example, we are allowed to describe whole intervals as possible values. We still have to explain why we see the pointer pointing in one direction. But changing the formalism, relaxing the formalism in that direction is promising to me. It's also promising to me to see new categorical formulations of quantum theory itself. But one thing I somehow fear, that's the nice reformulation, but it still has to. It just has to deliver on understanding. The physicists are not unhappy with quantum theory because teleportation looks ugly in Hilbert space language. It does look ugly in Hilbert space language. It's much nicer in this categorical language. It's yanking the rope. Well, that's really beautiful. That's not what's strange about it. It's really the main point is exactly what Einstein was pointing out. It does not describe reality, and Walt Heisenberg didn't even try to do that. They said, okay, we can't do better in principle. It's about experimental setups and what we can measure. Maybe Bohr is right, and maybe we do have to talk about the classical, the quantum world always in classical terms, but I doubt it, actually. Okay, but it is awfully hard to change the Hilbert space formula. This is another thing that it should be mentioned. Mathematicians would naturally try to generalize and say, okay, we drop one or two of these assumptions and let's see where this gets us. Do we get some nice generalized theory? In the mathematical sense, yes. In the physical sense, no. It's just a very rigid formalism. You say, okay, let's go from Hilbert space to Banach spaces. Everything is gone. We just can't do physics with that. And that's it. So probably the change has to be quite radical, which also means it's quite hard to achieve. Okay. Maybe it's a good time to have a coffee.
one thing for tonight,